Hello everyone, we're going to be doing our final review. These are going to be our practice examples. So we're at the very end of our course. If you notice, there are two final review documents. So we have this video where we go over practice examples, and then I have another document that just kind of highlights really the important things to get out of each chapter, and what things you should be able to do, and also things that you should understand for the final exam. So here we're just going to be doing some practice examples that I think are going to be very helpful when you go to take your final. So, and these are in any order. You'll notice that they do kind of follow the chapters that we have gone through, but maybe not every chapter. Some chapters are going to have more of an impact on the final exam, like how he said that chapter 9 is going to have more questions than any other chapter, and that's because we never had an exam on chapter 9. All right, so let's get started here. We have example 1, and this is asking us to use the logarithmic properties to simplify this problem into two logarithmic terms, and then we're going to solve for x. So we see here we have 1/3 times log base 5 of 27 plus log base 5 of 6 is equal to log base 5 of 2x plus 1 minus log base 5 of x minus 3. So we have a lot of terms here. We notice that each one of these terms has a log base 5, so they all have the same base. But remember, we want to use our logarithmic properties to simplify it, so we have two logarithmic terms. And when we say that, it's mostly that we just want to simplify one side, and then we're going to simplify the other. So, starting with our left side here, we have 1/3 times log base 5 of 27 plus log base 5 of 6. So the first thing that we want to do is that we can notice that this term here is using the exponential property. It's using the exponential property of logarithms. Since we see that the 1/3 is being multiplied by our logarithm, this means that 1/3 is an exponent of 27. So when we rewrite this, we rewrite it as log, oh gosh, it's very thin. Here we go. We rewrite this as log of 27 to the exponent of 1/3. And then everything else will be the same. So it's still log base 5 of 6 is equal to log base 5 of 2x plus 1 minus log base 5 of x minus 3. So now let's scoop this up just a little bit so we have a little bit more room. Now we want to simplify. So we see that this is supposed to be a 5, log base 5 of 27 to the power of 1/3. That's like saying the cube root of 27. Well, that's just going to be 3. So this is log base 5 of 3 plus log base 5 of 6. And now let's simplify our right side as well. So when you're simplifying these problems, you can do them in any order that you like, but we don't have a whole lot of room. So to save some room, I'm now going to go on to the right side and simplify there as well. So we see here on our right side, we're going to use our quotient property. And remember, our quotient property told us that if we have a log minus another log and they have the same base, we could rewrite this as log of whatever base it was of the first term divided by the second term. So when we rewrite this, it's going to be log base 5 of 2x plus 1 divided by x minus 3. So now I have this term. Now also we have the multiplication property. So now on the left side, we've simplified our very first term, so now we're going to use the multiplication property. And this is going to give us, so now whenever we see a log plus another log, that's like saying log of whatever you had on the inside times whatever product you had on the other. So this is going to turn into log base 5 of 18, since we're just multiplying the 3 and the 6. And that's what our multiplication property allows us to do. So now we have this log base 5 of 18 is equal to log base 5 of 2x plus 1 divided by x minus 3. So we see in our question here, that was our first thing that we wanted to do. We wanted to simplify the problem into 2 logarithmic terms. We now have 2 logarithmic terms. Now what we want to do is solve for x. So let's continue this over here. We have log base 5, 18 is equal to log base 5, 2x plus 1 divided by x minus 3. All right, so now we have these 2 terms, and we want to solve for x. Well, we can use the property of log base a of u equal to log base a of v is equal to u equals v. And this is because we see that when we try to cancel out the log, as long as they have the same base, it's going to simplify to whatever's inside the parentheses is equal to whatever's inside the parentheses on the other side. So if we use this property, this is just going to simplify. Let me say this is our little star here. And this will just simplify to 18 is equal to 2x plus 1 divided by x minus 3. We see our log base 5s completely go away because of this property. And this property specifically allows us to do this, but only because they have the same base. They both have a base of 5. All right. We also see that we had to simplify it to get this form because this does not allow us to have multiple logarithms on both sides. This only allows us to have one logarithm on each side of the equal sign. So what we did here in the very beginning, we had to simplify into 2 terms so that we could use this property, because we can't use this property if we don't have one term on each side. All right, so now all we have to do is solve for x. So it's going to be pretty easy. We just have 18 times x minus 3 is equal to 2x plus 1. This will simplify to 18x minus 54 is equal to 2x plus 1. So let's add 55 on both sides. Sorry, 54. Now you'll see what the answer will be. This is going to give us 18x is equal to 2x plus 55. Then we just subtract 2x on both sides. This gives us 16x is equal to 55, or x is equal to 55 divided by 16. So this number didn't exactly simplify down to an even number or even really a pretty number, because we see that this is going to simplify. If we want to put this in decimal terms, it's going to become 3.44. But that was going to be our value of x. All right. So now we've solved for x using logarithmic properties. So we can see here, just by looking at this problem, our logarithmic properties are extremely helpful and can really help us simplify a problem as long as this down to solving for x. All right, so now on to example 2. We have, if Mom and Pop's ice cream deposits $72 daily into a sinking fund for 2 years at 3.9% interest, find the final amount on deposit, and we're going to round to the nearest cent. So if we look at the definition of a sinking fund, The sinking fund is essentially just an account in which we can just start placing money. It's going to accumulate money. So we're not paying out funds, we're just accumulating. And then the money that is in the account is going to gain interest. So we know if we think about this, well, we should end up with a large number at the end of so many years because we've just been depositing money, we haven't been taking any out, and it's been gaining interest. So we're going to use the fact that a sinking fund forms an ordinary annuity. If it forms an ordinary annuity, we have a lot of equations for an ordinary annuity. And we want to find the final amount on deposit after 2 years. So what we're looking for is a future value. So our sinking fund, it forms this ordinary annuity. So let's use the formula for future value. Of an ordinary annuity. And this is a formula that is given to us in our notes and also in our book. And the formula, let's say formula is S is equal to R, where R is the payments, times 1 plus your interest rate divided by N, or your number of periods. And then you have, or sorry, this is M, and then we have N. So M, remember, is the number of times you'll compound in 1 year, and N will be your total compounding periods. Then we have minus 1 divided by, once again, I divided by M. So in this case, we want S. We don't know what S is. R is $72 because we're depositing $72 daily. Then we have our interest rate, which remember we want as I divided by M, is going to be 0.039 since our interest was 3.9%. And then we're going to divide by compounding periods. And remember, we're going to be depositing this daily, so it's compounding daily. So if it's compounding daily, we know that's 365 times a year. Then we have N, which is 2 years times daily, or daily for 2 years, is going to give us 730. So now we have all the terms that we need to plug into this formula. So we're going to get S is equal to 72 times 1 plus 0.039 divided by 365 to the power of 730 minus 1 divided by 0.039 divided by 365. So when doing these problems, it's really important to first identify what each one of these values in our question means. And then once we've established what they mean, it's really easy for us to just assign the values and plug them straight into our equation. Once we have this equation, all we need to do is plug it into a calculator and it will give us our answer. Remember, we're rounding to the nearest cent. So when we solve this problem, it's going to give us about $54,661.16. So by using this formula, it tells us that Mom and Pop's Ice Cream, if they're depositing $72 daily into a sinking fund for 2 years, had a 3.9% interest rate. After 2 years, we're going to have $54,661.16 in the account. Because remember, we're thinking about this account starting at 0. So if we're starting at 0, this is all the money that we're going to gain after 2 years by just depositing $72 every day. All right, so now on to example 3. Example 3 here is asking us to identify the operations the Venn diagrams are representing. So if we're just thinking about A here, remember we have our two sets which are represented by A and B as two circles. The rectangle is our universal set U. It was kind of missed there, but U. And then we see there's separate areas. So universal set is our entire rectangle. Our set A is the circle more towards the left. Our set B is the circle more towards the right. And then we see where they overlap, that is going to be the area that they share, and that they both contain elements. So what we want to do is identify the operations that the Venn diagrams are representing. So we're just going to focus on A for right now. If we're looking at A, this is going to come with a lot of intuition and a lot of understanding what Venn diagrams really are and what they represent. So if we're looking here, we see that the area that A and B share is empty. It's unshaded, which means that our set operation cannot contain the elements that they share. But they will contain the elements in each set that they do not share. And then they will also contain all the elements that are not contained in the set. So if we're thinking about this, we're really thinking about everything that is either in A and in B, but not in both, but is also in the entire universal set. And there's many ways that you can think about this. But remember, you really want to think about it in terms where we can have a set operation set up. So let's just take some notes. Let's just make some observations. So we see here that there is no shading in middle region. Or the region they share elements. And remember, the region that they share elements is going to be the intersection. So this technically means A intersect B. So our set operation cannot contain A intersect B. So we know automatically, well, that's not the case. But what we also see here is that we have our universal set, or the space in between our actual sets, is also colored in. So we say the universal set being shaded tells us one of our sets in our operation is a complement. Or really we should say that at least one is a complement, because that means that you would contain everything that's not in one set. But we see that A and B are both shaded. So you can't say, well, just A complement, because then nothing in A would be shaded. And you can't say B complement, because then nothing in B would be shaded. But we can say, well, what if they're both complement? If they're both complement, that means that everything not in A would be shaded and everything not in B would be shaded. So we can make another note. We can say that everything not in A is shaded and everything not in B is shaded. So thinking about what we just said is that everything not in A is shaded, but also everything that is not in B is shaded. The key word that we're looking for, as you see here, is and. And what this tells us is that we're working with a union. So if we're working with a union, this means that, remember, it's one or the other or both. So if we're thinking about this, we can start with A complement, because we know that's one part of it, and B complement. And so when we're thinking about this, remember, it's everything not in A and everything not in B, which only leaves the center unshaded. And this is going to tell us that it's going to be A complement union B. And that's our final answer, because we see that it's telling us, and we can even shade these in ourselves if we want to shade in. Oh, that is very, if we want to shade in A complement one color, and then we shade in B complement another color. If we shade in B complement, it's everything not in B. So when we color this in, it's just everything not in B. Then if we do A complement, remember, it's everything not in A. So if we're looking at this picture, we know it's a union because we see the areas that are pink and the areas that are blue are all shaded. So remember, that is one or the other or both. If it were an intersection, we would really only see the places where both colors touched would be shaded, which in that case would just be the universal set and nothing contained in either. All right. So now moving on to our second Venn diagram. So this one's very different. We're looking at the only shaded region is A. So we can say the only shaded region is A, but not the region with shared elements in B. So this tells us nothing in B, but something in A. So, and if we think about nothing in B, in each one of our set operations is going to contain A and B. These are our two sets. We can't just say, oh, just A. So when we look at this, if we're thinking of nothing in B, nothing in B is going to tell us B complement. But clearly, A is shaded. Oops, shaded. So we have A. Now, since we know what sets, when we're thinking of sets, we're really only thinking of A or A complement, or B and B complement. So we've decided, well, we probably have B complement and A. Now we just have to decide, is it a union or an intersection? So remember, union would be one or the other or both. So if we were thinking of one or the other or both, B complement would be shading in the entire rectangle. But if we're just thinking about A and B complement, maybe the intersection, remember that can only contain both. So we'll do the same thing here. We're going to shade in, sorry, this is just A. So if we shade in just A, we get this region here. Now, if we want to think about B complement, this is everything not in B. So this is going to be our entire region that doesn't include B. And if you see right here, this crescent shape of A is the only place that contains both colors, and that was the original place our Venn diagram was shaded. So this tells us that our answer is going to be A intersect B complement. So if you're ever confused, it's always okay to shade in your Venn diagram and see where your shading is going to match, and then decide which operator you want to use, whether that be union or intersection. So that's how I suggest you usually do these problems. You want to start with, are you thinking of A or A complement, B or B complement, and then once you have your two sets, then you want to try and find your set operator. All right, so now moving on to example 4. Example 4 here is telling us if a single card is drawn from an ordinary single deck of cards, find the probability it will be a black card or an even card. And our hint here is that we want to use the union rule for probability. So in cases where we have word problems like this, and we're thinking about set operations because we're thinking about the probability it will be a black card or an even card, then we're going to use our set operations, but we're going to use our set operations with probability. And we have this hint here, we're going to use our union rule for probability, so we know we're going to use that. So if we see here, if our question was asking us for a black and even card, we know that would be intersection because you use the word and, because that would just mean that it had elements of both. But this question here is asking us, find the probability it will be a black card or an even card. And that word or tells us it's going to be a union because it could be one or the other. But what our union rule for probability allows us to do is take out that factor of both because we don't want both. We're just finding the probability of a black card or an even card. So by using our union rule for probability, so we can write that first, union rule for probability. It's going to be the probability of, and we're going to set our variables. So let's say capital B is going to be a black card. Capital E is going to be an even card. Then we have the probability of B union E, or black card or even card or both, is going to be equal to the probability of getting a black card plus the probability of getting an even card minus the probability of getting both. And that's minus the probability of getting a black and even card. All right, so we have our union rule for probability. We've stated our variables, so now let's assign our values. So we see here we're going to have 26 black cards. And that's because our typical deck of 52 cards, half will be black, half will be red. So we have 26 black cards. So then our probability of pulling a black card is 26 out of 52, or 50%. Then we see that we want our even cards. And when we're thinking about even cards, we're thinking about non-face cards, because a face card can't be even. We're thinking about just the cards that are numbered 1 through 10. So if we're thinking about the cards labeled 1 through 10, or in this case, sorry, 1 is not in the deck, 1 would be considered an ace, but we won't consider, we will not consider the eighth. We're just considering the even cards. So that's going to tell us 2, 4, 6, 8, and 10. So it's going to be 10 even cards. Sorry, 20 even cards. 20 even cards in the deck. There's going to be 10 black even cards. So 20 even cards. And the way that you can even think about this is that because we're considering ace to technically be 1, and if you think about it, there's 12 face cards, 40 non-face cards, so 40 cards that are considered 1 through 10, and then you cut that in half and you have that many even cards. So we have 20 even cards. This is going to be our probability of pulling an even card is 20 out of 52. So then remember, we want to consider our black and even cards. So we're considering the probability of drawing both, or something that it has both elements. So if we're thinking about that, remember, like I said earlier, if you have 20 even cards in all, half of those cards will be red, half those cards will be black. So we know that there's going to be 10 black even cards. And that's the probability of B intersect E. And that's just going to be 10 divided by 52. So now we have all the elements that we need for our union rule for probability. So now we can just plug everything in. So we have the probability of B union E is equal to the probability of B, which is 26 divided by 52, plus the probability of E, which is 20 divided by 52, minus the probability of B intersect E, which is going to be 10 divided by 52. Now we can simplify this. This is going to give us 46 divided by 52 minus 10 divided by 52, so I just added the first two terms, or 36 divided by 52, which we can then simplify to 9 divided by 13. So then we can say the probability of B union E is 9 divided by 13. So 9/13 is our probability that that we will pull a black card or an even card. All right, that was how you would use your union rule for probability when using it for a question similar to pulling a card out of a deck. Okay. Now for example 5. What we're going to do is we're going to decide if the situation below should be calculated by a combination or a permutation, and then whatever we decide, we're going to calculate it. So our situation is, when purchasing an online mystery box from a clothing company, they informed me that by paying $35, you will receive a box of 7 randomly selected items from a catalog of 30 items. How many different ways can 7 items be selected? So we really want to take note of the wording of questions when thinking about, are we going to use a permutation or combination? So remember, permutation cares about order. They want to know the order in which things can be arranged. The combinations don't care about the order. So if we're thinking about this problem, we're just receiving a box with 7 randomly selected items from a catalog of 30. So we're randomly selecting 7 out of 30. And we don't really care about the order. It can be in any order, it's just the combination of it. So we can say the situation does not care about order. So it is a combination. And that's the first part. That was the first part of our question, was should it be calculated by a combination or a permutation? So we decided it's combination because it doesn't care about the order. Now we can move on to now calculating it. So we've decided that it's a combination. So now that we've decided it's going to be a combination, we're going to use combination formula with n equal to 30 because we're picking out of 30 items, and r is equal to 7 because we're randomly selecting 7 items. So this is going to give us our combination of 30, 7 is equal to 30 factorial divided by 30 minus 7 factorial times 7 factorial. And that's going to give us 30 factorial divided by 23 factorial divided by 7 factorial. Now, we can calculate this by hand, but it won't be very fun. So we're going to use our calculator for this. And when we do, we end up getting the value 2,035,800 different combinations of picking 7 out of 30 items. And we see here when we look at this problem, one number that we were given was that we're paying $35. So while the numbers 35 are in this problem, it is not relevant to our calculations. So even though the number 35 is there, it's completely irrelevant, so we just ignore it. We're only concerned with the 7 randomly selected items from a catalog of 30 and how we need to calculate them. So it's very important paying attention to the ordering of your question, because your number one thing in your mind when deciding to pick a combination or permutation is, will I care about the order? All right, so on to our next example. We have example 6. So for example 6, you're going to enter into a small lottery where a ticket costs $1. There are 10 prizes of $25, 15 prizes of $10, and 25 prizes of $5. You buy 1 ticket and a total of 100 tickets are sold. What's your expected payback? And we're going to round to the nearest cent if needed. So when we think about our payback, remember we're thinking about the expected value, or how much should our payback be over time? So it's not going to be by entering in this one lottery one time. It's going to be thinking about, well, if we entered this lottery for many times for a really long time, what should our eventual payback be? So remember to calculate an expected value. Your expected value is the value of some item, whatever you're thinking about, times its probability, and then you just keep multiplying and adding them until you get to whatever your last item is, multiplied by its own probability. Remember, that is our formula for expected value. And we know that this problem is expected value because it says what's your expected payback. So even though it doesn't use the word value, that's what it means. Payback means value. How much value are you getting back? So if we really think about this, then we know that we have 100 tickets total. There are 10 prizes for $25. There's 15 prizes for $10. There are 25 prizes for $5. And essentially, there's going to be 50 prizes for -$1. So you have 10 chances out of 100 of getting $25, 15 chances out of 100 of getting $10, 25 chances out of 100 of getting $5. You have 50 chances out of 100 for losing a dollar. So when we use our expected value, as we see here that we can really easily calculate our probability for each one of our values. And then remember, since we're thinking about payback, we spend $1 on a ticket so we can gain values or gain overall values of $24, $9, and $4, because we're essentially saying that we already spent $1 on our ticket, so our overall payback will be $1 less than each one of these prizes. Then our probabilities will be number of chances divided by 100, because we sold 100 tickets. All right, so now let's calculate our expected value. We've taken all of our notes, now we can calculate. So we're thinking about our expected value of X here. And starting with the chances of winning $25. There's 10 chances. Your payback is technically $24. So we start by saying 24. So remember, this is all about payback. So we have 24 times the probability that you will win. And remember, there's 10 chances out of 100 tickets. So that's going to be 10 divided by 100. Now we can add our second prize, which is going to be a payback of $9. And there's 15 chances you can win out of 100 tickets. So we have 15 divided by 100. Then we have the chance of being paid back $4, and there's 25 chances out of 100. Now we add our last value, and that is 50 chances of losing $1. So we would say -1 times 50 divided by 100. And now we can calculate these values. So we end up getting, and now I'm going to put these into decimal form. This is going to be 2.40, and we're rounding to the nearest cent, so we're just going to have our cents now. So we have $2.40, then we have $1.35 plus $1 plus -50 cents. And now let's add on our dollar signs. And if we just add up all of our positive terms first, we end up getting $4.75 minus 50 cents, which is going to give us $4.25. So our expected payback will be $4.25. And that's because with our small raffle, we had way more chances of winning than we had chances for losing. So our expected payback is actually going to be a gain. So if we did these raffles a lot for a really long time, we would see our overall payback is going to be around $4.25. All right, now for example 7. Example 7 here is we want to fill in the boxes of the extended table for a grouped frequency distribution using the fact that the mean, or X bar, is 22.8. Then we're going to calculate the standard deviation and round to 2 decimal places. So we see here we have a grouped frequency distribution, and this is the extended table that we really like to use when we want to solve for standard deviation. So normally when you're given these tables in your book, you're really only given maybe the first two, and if you're lucky, the third column. But what I really like to do is to add these additional 3 columns and just make it really easy and straightforward on what we need to be calculating in order to find our standard deviation. In this case, we're just filling in some of the boxes. So we see that a lot of the boxes are already filled in, and we just need to fill in a few. So if we pay attention to our table, we see we have intervals from 10 to 16, 17 to 23, and 24 to 31. Then we have our frequencies. So we see our frequencies for the interval of 10 to 16 is going to be 2. Our frequency for 17 to 23 is going to be 5. And our frequency for 24 to 31 is going to be 8. Then we have our midpoints. So remember, our midpoints would be our lower value plus our higher value divided by 2. So it's basically just the average or the mean. So we have 13 as our first midpoint, 20 as our second midpoint, and 27 as our third midpoint. Then we're calculating x minus the mean in our fourth column there. And our first spot is blank, so this is the spot we're going to be filling in. But we can really pay attention to the second two. And remember, our mean is 22.8. And we can even just follow the title in our column, which is x minus x bar. Our midpoint we know is x, or 13. So this is going to be 13 minus 22.8, which is going to give us a value of negative 9.8. And actually, we don't need all that stuff written. You know it's going to be 13 minus 22.8. And I'm going to highlight that again so we knew which box. And now let's go on to our second column, because that was the only box that was missing. So now in our second column, we just have x minus x bar squared. So it's the same value that we found in our previous column, it's just now that's squared. So in the box that we have here, all we're doing is taking negative 2.8 squared. So if we just calculate negative 2.8 squared, we're going to get a value of 7.84. And that would be the answer in that box. And you can always check to make sure. You could always square each one of the other terms to make sure that it all checks out. And then we have our final column. So we have x minus x bar squared times f, our frequency. And what we're really seeing here is that we're building upon every column. So our first column, we had a value, then our second column, we squared that value, and then from that column, we multiplied by our frequency. So we're building on our columns. So now for our our sixth column, if we're considering all the columns. In our sixth column here, we're going to take our frequency and we're going to multiply it by the results we found in our last column. So we see in our first row, we have 192.08. That is just 96.04 times 2, or frequency of 2. Then we see that 39.2 is just 7.84 times 5. So for our last row, what we're going to do is we're going to take 17.64, we're going to multiply it by 8 to find our our x minus x bar squared times our frequency. So once we calculate this value, it's going to give us 141.12. Now we can just add all of these values together, and we're going to end up getting our answer here. going to get our total value of 372.4. And that is just the sum of our column. Or remember, we write this as the sum of x minus x bar squared times f is 372.4. So we finished our first part of this question. We filled in all of our boxes and we filled them in correctly. Now we just need to calculate the standard deviation. And remember, our formula or standard deviation formula is the square root of the sum of x minus x bar squared times f divided by n minus 1, where our frequency is n, or our total frequency. Another way we could just say the frequency of f is equal to n. So in this case, we have n is equal to 15. So when we rewrite this, and remember we have this value that's in our numerator. We already found it by using our table. It's going to be 372.4. So when we rewrite this, we're going to have 372.4 divided by 15 minus 1. Or 372.4 divided by 14. And all we have to do is put this into a calculator. And this is going to give us 5.158. And remember, we wanted to round to 2 decimal points. So we can say that this is going to be about 5.16. So our standard deviation is 5.16. So we see that when we have a table like this and it's pretty much filled out, or it's really close to being filled out, it's going to be really easy for us to solve for our standard deviation. Now, if we didn't have, let's say, the last 3 columns filled out, there would definitely be quite a bit of work to end up finding this answer. But it's a very organized way of making sure that you know what your standard deviation is going to be, ensuring that it's going to be correct. And our question also gave us the mean, which was very helpful. All right, so now on to our very last example. This is example 8. It's telling us that we're going to find the z-score for x equals 23 if a normal distribution has a mean of 41 and a standard deviation of 14. We're going to round to 2 decimal places. So specifically, when we were talking about z-score, there was also a lot where we talked about the corresponding area under the normal curve. And remember, that was where we used all of our tables, we found our z-scores, and we found the corresponding area using the tables, and there was a lot of table work. And when it comes to something like a final, we test concepts, not how well can you read a table. So for example 8 here, what we're really just looking for is finding the z-score when given a mean and a standard deviation, which we can do because we have a formula for this. So we can say that our z-score formula is, remember, z is equal to x minus mu divided by sigma, where mu is the mean and sigma is the standard deviation. So we have a formula for our z-score. And this question is very straightforward. It's just asking us to find the z-score for x is equal to 23, so that's our x value, if a normal distribution has a mean of 41 and a standard deviation of 14, and we're going to round to 2 decimal places. So we're just going to use this formula to find our z-score. So when we do this, we're going to get z is equal to 23, so that's our x value, minus our mean, 41, divided by our standard deviation. which is 14. And now we just calculate. So when we subtract 41 from 23, that's going to give us negative 18 divided by 14. This can simplify to negative 9 divided by 7. And when we actually find this value, because we want it in terms of decimals, and we round to 2 decimal places, this is going to give us negative 1.29. So our z-score is negative 1.29. Something we notice about our z-score is that it's going to be negative, which means that this means we're looking at our z-score, which is going to be to the left of our mean in our curve. We see it's more than 1 standard deviation less than the mean. So we know that our area under the curve is most definitely going to be below 50%. All right, so those are all the examples that I felt like would be very beneficial to you when studying for your final exam. So remember, definitely go over the other document that was posted. You really want to look at those too, because those tell you what exactly you really want to know and what things are most important, as well as doing examples like these to really prepare you for your final exam. All right. As always, if you have any questions relating to our final review or any questions about your final in general, you can always feel free to pop into my office hours, which are going to be my last office hours today from 1 to 2:30, or you can send me an email. You could use the anonymous homework question form, but I don't think it would be very helpful since I won't be making another video. So I highly suggest popping into my office hours or sending me an email. So thank you all for a lovely time in these last 5 weeks. I know it was a lot. I know it was really fast, but it was a lot of learning that we definitely did. All right, so maybe I'll see you all in the future, maybe not virtually as well. So good luck on your final.